Welcome back. Now we are finally ready to discuss about the aliasing effect. So just to recap what we had seen in our previous video, we discussed about the downsampling, and we had also discussed about the fault line, and we saw that as long as the spectrum of the signal is away from the fault line, when I do the downsampling, then nothing happens to the integrity of the spectrum itself. But the moment the spectrum falls or overlaps over the fault line, then we are going to see the aliasing effect. So now we are going to discuss that how we are going to see this aliasing effect. Okay, so I've got this diagram already here. So what it says is I've got a spectrum here, which has it is a band limited signal which has got this spectrum with maximum frequency, and as you can see that it is reasonably far away from the maximum digital frequency fs by 2. Okay, that can represent, and we also know that, well, all the frequencies above fs by 2 are simply the image frequencies. Okay, and we had also discussed that as you keep on increasing the frequency, and along with that, if you change the sampling frequency, this is simply the periodic in nature. So if you keep going up to infinity, the spectrum is simply going to repeat. Okay, it's just the replica. So in this example, we have taken the spectrum which is already sampled at certain rate, and we call it as 1x. Okay, and this is the fault line. So we had seen that if you downsample, right, so it is as good as either it is absorbing, so all the points are getting absorbed around the fault line, or in other words, we can say that, well, we are actually moving the scale of the fault line fs by 2 and the other scale of fs and all the corresponding scales in this direction. And in this during this process, all the points that are falling here, they simply gets absorbed around the fault line. But in this particular example, as we can see that we do not have any points around the fault line. So as long as I downsample, so I'll just change the color here. Okay, so as long as I downsample, and so let's say I'm doing downsampling by a certain factor. It is not exactly up to the scale, but just for the sake of understanding, let us say that I have downsampled, and as a result, it has absorbed these many points. Okay, so what we had seen in the previous video was that the spectrum is going to remain as it is, but the fault line is going to move. Okay, so now this is fs by 2 is going to sit here, and then I'm going to have the image frequencies, corresponding image frequencies sitting here. Okay, so that's what we had seen. So this will be fs, this will be fs, or we can call it as f dash of s as a new sampling frequency, right? And we had seen that up to this point everything was fine as long as they do not overlap, these two components of the spectrum do not overlap over each other. But now let us take the conditions where you downsample so much that there is going to be some issue, and we will see that what actually happens when you downsample beyond this point. Okay, so okay, let's call this guy as okay, we'll take a new sampling frequency, and let us say I'm downsampling this thing by factor of 2. Okay, so I'll just change the color here. So I'm downsampling by factor of 2. Okay, so I'm downsampling this guy. So this is at 1x, and I'm going to have x by 2 sampling rate. Okay, I'll call it as x by 2. And so now what happens? So now let us put it to the original scale. So this was my original samples, right? This point was originally fs by 2, and this point is approximately here, so this is fs, correct? And the spectrum was we had seen, well, this is how the spectrum was. Now I am downsampling it by factor of by 2. So if I downsample, then my new sampling frequency fs, or I will call it as f dash s, is going to fall here, right? This will be a new sampling frequency, and its corresponding half f dash of s is going to fall here, f dash, so it is f dash s by 2 is going to fall here, correct? So now let us map this spectrum. Let us map the spectrum here and try to see what actually happens when you downsample. Now as we can see that, well, okay, this is the fault line, right? We know that, well, this is the actual fault line, and all the points, so basically I'm going to move in this direction, and if you see the original spectrum that is sitting here, let me replicate the original spectrum as well, so that we can get a clear understanding. So this is the original spectrum that used to be something like this, right? And the image is looking something like this here. Now I'm moving in this direction. Now see how far I am moving. I am moving up to here. So now what is going to happen is it is going to absorb all the points that are sitting around here. this guy is moving in this direction, so it's going to absorb all the points that are sitting around here. Now what happens when it crosses the threshold? What happens when it crosses this threshold? Because I'm not just moving here, I'm not finishing up to this point, I'm moving further. I have to end up here. So in this case, all the points which are sitting here, right, all the points which are sitting here, and its corresponding image also we can take. So all the points which are here, right, this guy is going to move in this direction, so they will simply accumulate around the fault line. Okay, and when they accumulate around the fault line, I'm going to get a new spectrum, and the new spectrum is going to look something like this. So the integrity of the spectrum will be maintained up to certain points, which will be up to this point. And then what happens is that these points around the fault line, okay, so now my fault line has come here, the final fault line is now sitting here. So around the fault line has absorbed all these points and they will be accumulated together. So I'm going to have an effect something like this. Okay, I'm going to see something like, so let me make the other part of the spectrum as well. So it is going to look something like this, and there, this is a point of accumulation. Okay, so the integrity of the signal at these frequencies also will be maintained, and this will be the overlapping part. Okay, this will be the overlapping part. So here we see, so this part that we call as the loss of the spectrum. The spectrum is losing its original identity. Okay, what happens here is that the spectrum is overlapping over each other and we are having an aliasing effect. And that is what we call as the aliasing because of the downsampling. I hope this makes sense to you. In the next video, we will look at some numerical examples and we will see how we can see it numerically, all the effects that we have explained it here. Okay, so I will see you in the next video, and we'll also try to do some analytical derivations as well. Okay, but at this moment in time, as we build up the case after the case, okay, we'll come to the analytical derivation later once we have the solid understanding of the basics first, and then we'll look into the analytical formulas. Okay, so I'll see you in the next video.